Hello, I am Biswaksen Patnaik. I'm a PhD student in the Department of Computer Science at the University of Maryland, College Park. Today, I will be presenting our work, VisTorch Interacting with Situated Visualizations using Handheld Projectors, that I co-authored with Dr. Huaishu Peng and Dr. Niklas Elmqvist. Spatial data is best analyzed in situ, but existing mixed reality technologies can be bulky, expensive, or unsuitable for collaboration. Implementing ubiquitous displays is a non-trivial technical challenge, with each solution having its own drawbacks. For example, fixed displays are static, whereas mobile displays are typically limited in size, thus limiting the display area and the potential for data embedding. Augmented reality using head-mounted displays is nearly ideal for this purpose, but such displays are costly, cumbersome, and have a personal screen. Even handheld AR, which is trivial using current mobile devices, is troublesome because the imagery is shown on a personal screen, making establishing diaxes and common ground between collaborators awkward. We present VisTorch, a handheld device for projected situated analytics. It is a camera projector system that reads fiducial markers placed in the environment and projects a perspective correct display on the surface. It provides a hand-controlled people interaction in physical space, affording didactic gestures. This enables embedding data visualizations in physical space. There are three primary components to the VisTorch hardware: a laser projector for displaying visual contents, a camera to read Aruco markers, and a trackpad to facilitate interaction. We use Aruco markers placed on flat surfaces in the environment to enable tracking the position and orientation of the device. We calculate a perspective transform to apply to displayed imagery. This makes it possible to render distortion-free view of any data visualization in part of the space, even if the device is held oblique to the surface. Small movements induced due to unstable hand movement causes the display to be jittery and difficult to read. To avoid this, we employ a moving averages-based smoothing technique to stabilize the image. The user interface of the VisTorch system is rendered in the browser and is built with standard web technologies, HTML, CSS, and JavaScript. VisTorch is compatible with any web-based visualizations. We show the interaction features of the device. The projection undergoes a corrective transform such that it looks pinned to the physical space. The corrective transform corrects any skew induced due to an oblique angle of projection. Different surfaces act as placeholders for placing visualizations. A visualization from a predefined list can be placed on any surface. Visualizations placed on any surface are tagged to it. We conducted an experiment to evaluate the user experience of VisTorch. The purpose of our study was to determine if the affordance of placing visualizations in physical space helps create didactic metaphors that enhance embodied and distributed cognition. Participants were given a list of visualizations that could be viewed with VisTorch. Our experiment involved two sense-making tasks: layout generation, that is placing and arranging visualizations in physical space for an initial exploration, and identifying data items for the created layout. We recruited 20 paid participants for our study, 13 identified as male and 7 as female. The age of the participants ranged from 21 to 35 years. Most participants were university students except 2 who were working professionals. The experimental factors for our study were view cardinality and data type. View cardinality is the number of visualizations required to complete a specific task, such as 1 view, 2 view, or 3 views. For example, a 2-view task would require combining findings from 2 separate visualizations to answer. Data type refers to the type of data involved. Non-situated refers to abstract data where physical location has no significance. And situated refers to context-specific data placed near physical referent. The study was conducted in a space that resembled an office setting. The study sessions were audio and video recorded. Participants were asked to think out aloud during the study. Participant-authored organizational layout was recorded in time and space. We also recorded how the system was used in situ. After the tasks, participants were asked to fill a NASA TLX questionnaire. We analyzed the collected data using an inductive approach. We observed three broad organizational strategies employed by the participants in the study. Strict categorical clustering. We observed 70% of the participants strictly following a categorical clustering technique where they placed one copy of all the visualizations in specific self-authored clusters. Here, the participants made clusters of distinct categories and preferred to move between these clusters while performing tasks, such as referring to a visualization or comparing between two visualizations from different clusters. Redundant clustering. We observed a pattern where 30% of the participants made not only unique categorical clusters, but also used multiple copies of the same visualization that they believed were relevant in context. Situated clustering. We noted that all participants prioritized the immediate vicinity of the artifacts in placing visualizations that describe the artifacts. Diaxes in guided presentation. Participants often use didactic metaphors when presenting an overview of their layouts. Spatial arrangement and mental models. Participants mentioned the importance of self-authored layout of visualizations, which helped memorization. Authoring ad hoc dashboards with direct manipulation. Participants stated that self-authoring visualization dashboards gave them freedom in arranging space, sometimes even on the fly. We also performed an expert review with 4 professionals drawn from various fields with situated data to derive realistic and practical usage scenarios for VisTorch, such as in museum tour guides, set design for theater, learning outside classrooms, and collaborative brainstorming. E1 is a creative technologist and educator at the Smithsonian Museums who designs AR museum guides. E2 is a projection media designer who specializes in cinematography, analog-digital hybrid puppetry, and immersive performances at a performing arts center. E3 is an environmental education coordinator who works with the School of Conservation that fosters environmental knowledge through education programs delivered in natural settings. E4 is an economist and information science PhD who develops statistical software. Spatial reasoning. Experts remarked on the use of VisTorch to support spatial reasoning in situated data. E1 mentioned using VisTorch in museum tours to show shapes and patterns in paintings that may be invisible to the untrained eye. E2 remarked on spatial arrangement in set installation by crew, where VisTorch could be used to project the set plot. Engagement and efficiency. Experts remarked on the use of VisTorch for increasing engagement of the audience. E3 noted that VisTorch affords a dynamic way of presenting data in situ that keeps students engaged. Collaboration. Experts noted the utility of VisTorch for collaboration. E4 mentioned using VisTorch for collaborative brainstorming. While VisTorch has all the affordances needed to author situated visualization dashboards in the real world, our implementation has room for improvement. As VisTorch has to be held at all times, one hand is captive, restricting bimanual interaction. While VisTorch is tethered, a future version may have processing on board. The image stabilization on VisTorch induces a small latency. A future version of VisTorch may incorporate IR fiducials, or other improved surface detection techniques to eliminate the need for fiducial markers. In summary, we presented VisTorch, a handheld device for projected immersive analytics in physical space. Thank you.